Okay, perfect. All right, guys. So yeah, so last week, I mean, we discussed a little bit, conservative vector fields, and uh, so let me just remind you what we said last week about conservative vector fields. So first, what's a conservative vector field? So we said conservative vector field is a vector field of the form the gradient of some function f, right? So vector field f capital F of the form so capital F equal to the gradient of some scalar potential function f, okay, of gradient of some potential function f, okay, lowercase f, is called conservative vector field or a gradient vector field. Okay, so conservative vector field, or if you prefer, a gradient vector field. Right. So we are interested in the conservative vector fields because we said, I mean, we proved last week that the conservative vector field has a path independent line integrals. So the line integral of f depends only on the value of the function, the scalar function at the endpoints of the path, right? So we said, so f, so conservative vector fields are special because, well, they have path and dependent line integrals, right? So that's what we said last week. Line integrals, vector line integrals. So the line integral of f, we said, would depend. So the line integral of f capital F, the vector field, depends on the value of the function at the endpoints of the path, right? So depends on the value of the scalar function f of lowercase f, okay, at the endpoints of the path. Okay. So that's what we discussed last week. So I think on last Thursday, we had we tried to answer 2 questions about these conservative vector fields. So first question was, how can we determine whether a vector field is conservative, right? And the second question was, if we know, assuming vector field f is conservative, how can we find the potential function f, right? Such that the vector field would be the gradient of f, right? So we had 2 main questions to answer. So the first question was, how can you determine whether f is a conservative? Okay, whether capital F, the vector field f, is conservative, is a gradient vector field, all right? And the second question was, assuming f, assuming that the vector field f is conservative, assuming f is conservative, okay. So the question is, how can we find the potential function f? So how can we find the scalar function f, right, such that the vector field f equal to the gradient of f, right? So such that the vector field f equal to the gradient of f. Okay. I think we answered the first question, but we didn't have, I think, examples. So today we're gonna do plenty of examples, and we're gonna also try to answer the second question. So the answer to the first question was, so we said that so roughly speaking, if the curl of the vector field f is 0, then the vector field f is going to be a gradient vector field, right? So so the answer to the first question okay, so we said so roughly speaking, if the domain of the vector field f suppose that the domain of the vector field f, capital F, is simply connected. So we said, roughly speaking, simply connected means that the space it's just a one single piece with no hole, right? So simply connected. Okay. Either it's a region in the plane or in the space, right? Either in R2 or R3. Then F, so in R2 or R3. Okay, and so then F is a conservative vector field if and only if the curl of F is 0. So curl of F, we said it's just the cross product of the del operator, the nabla, with cross product with the vector field F. So we need this curl to be 0. So cross product gives you vector field, right? It's a vector. So we need the curl of F to be the 0 vector, okay? At all the points of course, of the domain. Okay. And then we said, in the case of the two-dimensional vector field, so if my vector field is defined in the plane, so it's given by two functions. So we said, so let me just remind you what we said the last time, I think at the end of the lecture. So we said if the vector field F, in case of if F, the vector field F is a two-dimensional vector field, so it's given by two functions, M and N, right? Then curl of F equals to 0, okay? If and only if partial N, partial X, derivative of N with respect to X is equal to the derivative of M with respect to Y. Okay. And so this is the case of the two-dimensional in the two-dimensional for two-dimensional vector fields. Now, so today we're going to see a couple of examples. I think we stopped here, right, with this remark. So today let's do a couple of examples and exercises. So, okay, let's start with the first example. Two-dimensional. Again, so I'm going to do a two-dimensional example and then a third three-dimensional example. Okay, so examples. So first example, as I said, it's a two-dimensional vector field. So let's say the vector field F is just xy. Okay, this is equal to xy. Okay, so what we are saying here is that the first component, my function m, is equal to x, right? And my function n is equal to y. Okay. So this is my two-dimensional vector field. And the question, of course, is to determine whether f is conservative, right? So the question is determine whether f is conservative. Okay. All right. So in this example, I mean, the domain of this vector field f is just the whole plane, right? I mean, the function x and the function y that are defined in R2. So the domain here is just the whole plane. It's R2. Okay. And R2 is, you know, it's simply connected. So in the case of two-dimensional vector field, guys, so by the remark we had, so the only thing we have to check is that the derivative of n with respect to x is equal to the derivative of m with respect to y. So in that case, the vector field would be conservative, right? So so if we use our remark, so by our remark, so all we have to check is, so we have to compute first partial n, partial x. All right, so derivative of n with respect to x. So n is, so n xy is just equals, that's the second component of the vector field. So the function n of xy is just equal to y, right? And the function m, the first component, is equal to x. Now, all we have to do is to compute the derivative of n with respect to x. So n is just y, there's no x, y. So when we derive with respect to x, you consider y, we assume y as a constant. All right, so the derivative of a constant, of course, would be 0. So derivative of y with respect to x is just 0. Right, so this is just equal to 0. Please let me know, guys, if you have any question, right? You can stop me at any time if you feel free to answer to ask questions, right? Now, what about the derivative of m with respect to y? Okay, so as I said, we need to compare derivative of n with respect to x to the derivative of m with respect to y. Okay, now m is equal to x. Okay, so when you derive with respect to y, you assume x as a constant. So then derivative of a constant is just 0. Okay, so the derivative of m is equal with respect to y is 0. So the conclusion here is that, so the partial derivatives here, the derivative of n with respect to x is equal to the derivative of m with respect to y. So both are equal to 0. Okay. So if the derivative of n with respect to x is equal to the derivative of m with respect to y, right? Then we can conclude that the curl of curl of f, the vector field f is 0, is the 0 vector, and so your vector field f is a conservative vector field. Okay, so then curl of f is 0. So we conclude that, we deduce that f is equal to the gradient of some potential function f, right? So that f is conservative. Okay, if the partial derivatives are different, right? Then of course, then your vector field F is not conservative. Okay. So again, so just to remark here, so if the partial derivatives are different, so if derivative of n with respect to x is different from derivative of m with respect to y, then this vector field F is not, then F is not conservative, right? And so this is my, so this is our first two dimensions. The first example is just a two-dimensional vector field, right? Any question, guys, about this example? So it's whenever you have a vector, two-dimensional vector field, so we have two components. First component is M, second component is N. So if you want to see if your vector field is conservative, all you have to do is just to, compare the partial derivative of n with respect to x to the partial derivative of m with respect to y. Okay. Now, second example. So we're gonna do. So this is a two-dimensional vector field. Now we're gonna have an example with a three-dimensional vector field. So example number 2. So let's say capital F, our vector field F. So x, y, z. Okay, so we're gonna have 3 variables. So this is a three-dimensional vector field. So we have 3 variables. So let's say the first component is 3x squared. Second component is z squared over y. Okay, and the third component is, let's say it's 2z natural log of y. Okay, so this is our vector field. Okay, so you can check. So the domain of this vector field is actually simply connected. So domain of F here. So just be careful. So, so the first component or the first function here, 3x squared, the domain of this function, it's defined for any, for any x here, x, y, z. But then for the second component, we have to remove the case when y is equal to 0, right? Because we are not allowed to divide by 0, right? So y has to be different from 0. And then in the third component, we have natural log of y. And as you know, natural log of y, natural log of x is defined for, positive real numbers, right? So the y has to be a positive number, right? So the domain would be domain of F here. So that's the triple x, y, z, such that y is positive. Okay, so we need y to be positive. Okay. Anyway, so I claim that this domain is simply connected. Okay, so this is simply connected. All right. So now, so the question is, of course, is to see whether F is a conservative, right? So, so the question is determine whether F is conservative. Determine whether F, the vector field F is conservative. Okay. So what we need to do in this case, by the answer to the first question, we said that, I mean, the F is going to be conservative if and only if the curl of F is the 0 vector. So we have to compute the curl of F, right? So we need to check. We need to see if the curl of F is the 0 vector. So we need to evaluate curl of F. So that's the cross product the cross product of the del operator with the vector field F. Okay, so again, let me just remind you the del operator. You can see the del operator as a vector field, so it's just partial x, partial y, and partial z. Okay, that's the del operator. Okay, so the curl of F, so cross product. So first row, in the first row, we're gonna have I, J, K, right? So let me just remind you. So I is just the vector 1, 0, 0. J is the vector 0, 1, 0, and K is the 0, 0, 1. Okay. Second, in the second row, we're gonna have the del operator. So that's the partial x, partial y, and partial z. And finally, in the last row, we're gonna have the vector field F. So vector field F is, the components are given by, so it's 3x squared, z squared over y, and then 2z ln of y, right? So in the last row, we're gonna have 3x squared. Okay. The second component is z squared over y. And the third component is 2z natural log of y. Okay. So we need to compute the cross product. So this would be equal to, so what would be the coefficient of I? So for I, we're gonna cross multiply, the partial y with the derivative with the 2z natural log of y. So that would be the derivative with respect to y of the function 2z natural log of y. So it's 2z natural log of y minus, and then we have derivative with respect to z of the z squared over y, right? So minus derivative with respect to z of the z squared over y, all right? So that's the coefficient of I, the vector field the vector I. Now for j, so we're gonna have, let's say, plus here j. Okay, so what will be the coefficient of j? So we have to cross multiply. So this derivative with respect to z of 3x squared minus derivative with respect to x of the 2z natural log of y. Okay, remember guys, for j, if you put a plus here, okay, then you should start with this, let's say, with this term here. So the derivative with respect to z of the 3x squared, minus, and then derivative with respect to x, of 2z natural log of y. Okay, and then the last component, so plus here, so we're gonna have the k. And so what will be the coefficient of k? So we're gonna cross multiply here. So derivative of x, derivative with respect to x of z squared over y. So that's the derivative with respect to x of z squared over y. Okay. Minus derivative with respect to y of the 3x squared. So minus derivative with respect to y of the 3x squared. Okay. So that's the curl of the vector field F. Okay. Now let's compute. so for the coefficient of I, guys, first we need the derivative with respect to y of the 2z natural log of y. Okay, so when you derive with respect to y, so I'm talking about this term here. So derivative with respect to y, so we assume that z and x are constant, right? So all we have to do here is to compute the derivative of natural log of y. Okay, so natural log of y, derivative of natural log of y, it's just 1 over y. And the 2z is just constant. So it's going to be the constant times 1 over y, right? So this is the constant, which is 2z times derivative of natural log of y, it's just 1 over y, okay? Minus, and then the second term here, this one here, it's derivative with respect to z, so we consider y as a constant. So y the denominator, but it doesn't matter, it's just constant, so we don't worry about the y. So we have to derive the z squared. So derivative of z squared, of course, is just 2z. So it's going to be 2z in the top minus 2z in the top, and as I said, y is a constant, so it's just I'm going to have this y here in the denominator. Okay, so this is times the vector I. Now, what about the coefficient of the vector j? First, derivative with respect to z of 3x squared. X would be constant, so the whole thing is going to be constant with respect to z. So then the derivative is 0. So that's just 0 minus, and the same thing here for this 2z natural log of y, derivative with respect to x. There's no x, so everything is just constant. Y and z both are constant. Derivative would be then just 0. Okay, and then for the last component, so this is plus. Here's my k. Same thing. Derivative with respect to x of this z squared over y. So z and y both are constant. So derivative with respect to x would be just 0. So that would be 0 here minus, and the same here. 3x squared, derivative with respect to y, we assume x to be constant. So that would be just, derivative would be just 0. Okay. So the component of j, component of k, both are 0. Now for the coefficient of I, we're going to have 2z over y minus 2z over y. Okay, so this is just so here this is just 0, just 0. All right. For the first one, the same thing. It's just 2z over y minus 2z over y, right? Times the vector I, which is 0. So this is just 0, so that'll be equal to the vector field. So the whole thing is just 0 vector. Okay. So the conclusion is that the curl of f is the 0 vector, and so f is conservative. Okay, so then conclusion. So curl of f is equal to the 0 vector. As I said, it's a curl of f. It's a cross product, so it's supposed to be a vector. So curl of f is the 0 vector, then f. So then f is the vector field f is conservative. Okay. So this is a 3-dimensional vector field. So this is how we determine whether f is a conservative, right? So all we have to do is to compute the curl of f. Any question, guys, about this example? So just be careful with the partial derivatives, all right? Okay, so if there's no question, guys, so here's an exercise. So I'm gonna give you a couple of vector fields, and you need to check whether f is conservative or not. Okay, so exercise. So you have to determine whether f is conservative. Okay, so let's start with a two-dimensional vector field. One f is equal to, so it's two-dimensional, so we're gonna have two variables. So it's just let's say x squared y minus 2xy. All right. Second vector field. It's a three-dimensional vector field. So f of no, let's do another two-dimensional example. So f of xy is equal to let's say 2xy plus cosine of 2y. Okay, this is the first component. The second component is x squared minus let's say 2x sine of 2y. Now, last problem, as it will be a three-dimensional vector field. So f of x, y, z is equal to x over x squared plus y squared plus z squared, okay, minus 6x. That's the first component. A second component is y over x squared plus y squared plus z squared, right? And the third component is z over x squared plus y squared plus z squared. Okay. All right, guys. So I'm gonna give you, let's say, 10 minutes, about 10 minutes to think about this exercise. Again, for the two-dimensional case, when you have two-dimensional vector field, all you have to do is to compare the derivative of the n with respect to x to the derivative of m with respect to y. In the case of three-dimensional vector field, well, you have to, compute the curl of the vector field there. Okay, so say you have 10 minutes, guys, to think about this exercise, and if you have any questions, just let me know. All right, I'm here to answer your questions. Right, Anisha, David, any idea about number one? You know if F, the vector field F in number one is a conservative or not? Okay, probably guys, you need more time, I guess. So after this exercise, guys, we're gonna try to answer the second question, which was assuming f is conservative, how can we find the potential function f, right? So I will show you some examples how to find the potential function f. And then I guess we're yeah, and then I guess we're gonna be done with this section, conservative vector fields, and then we're gonna move to the surfaces, okay, and then we're gonna move to the parameterization of surfaces, and then Stokes and Gauss divergence theorem. All right, so I'm gonna give you a couple of more minutes, and then I will go over the exercise. So as I said, guys, I mean, in practice, I mean, in the homework or the test, you don't really have to. I mean, the domain of the domain of your vector field f is gonna be, well, I mean, in theory, you need to check that the domain of your vector field f is simply connected. But I mean, in the as I said, in the homework or in the test, um, it already, I mean, the domain is gonna be simply connected. I mean, you don't have really to worry about the domain, okay? But as I said, in order to apply our theorem to check that the curl of f is 0, you need the assumption, the hypothesis that the domain of f is simply connected. All right, guys. I mean, I don't know if you I mean, you had time to check this exercise, but anyway, so I'm gonna just go over the problems here. For the first vector field, as I said, it's just a two-dimensional vector field. So for number one, well, the domain here of the vector field, I mean, the components are x squared times y and minus 2xy. So this is defined for any x and for any y. So the domain here is just the whole plane, it's R2. And as we said, R2, it's of course simply connected, right? So the domain of F is R2, and it's simply connected. Okay. So first component, that will be my M. So this is my M function M. Second component, that's my function N. So we have to compare partial N, partial X. So you assume Y as a constant. And so derivative of N with respect to X, that will be minus 2Y. Right, so this is minus, minus 2Y. Right? And for derivative of M with respect to Y, okay, so you assume X as a constant. So the X squared is going to be constant. So then derivative of X squared times Y, it's like derivative of some constant times Y. So that will be equal to the constant, which is X squared. Okay. Now, if you compare these two functions, of course, they are different in general. So, so then partial N, partial X, this is different from partial M, partial Y. All right, so then, so F is not. So the function, the vector field F is not conservative. Okay. For number 2, the second vector field is again the two-dimensional vector field. The domain again here, so the functions here is just so we have 2xy, we have so 2xy, this is defined for any x for any y. The domain of the cosine, domain of sine, they're just they're defined for any x and for any y. Okay, so the domain of the second vector field is again is just R2, which is simply connected, right? So we can check. We can compare. So for number 2, so the n, the function m. So that's the first function, of course. So m. So m of xy, that will be the first component. That's 2xy plus cosine of 2y. And the second component, that's my n, capital N. That's the x squared minus 2x sine of 2y. Okay, and so we have to compare. So we have to compute partial N, partial x. All right. So derivative. First, we have derivative of x squared with respect to x. That will be 2x. So here we're going to have 2x minus, and then this is sine of 2y. Y is, we assume on y as a constant. So sine of 2y is just constant. There is this 2 here. It's also constant times x. So derivative of some constant times x, that will be just the constant, right? So that's minus 2 sine of 2y. Now derivative of m with respect to y. So we assume x as a constant. So here, this x here is a constant. So 2x is a constant times y. So the derivative with respect to y would be just equal to the constant. So that's 2x, right? Plus, and then cosine of 2y. So cosine of 2y, derivative with respect to y. So here we need to apply, you know, this is a composition of two functions. There's a function cosine and there's a function 2y, right? So we need to apply the chain rule. Okay, so if you want to compute the derivative of this thing here, the cosine of 2y with respect to y, you need to apply the chain rule. So if you apply the chain rule, then you know, this is like the cosine would be like your function f, and the 2y would be your function g, right? So the chain rule would give you g prime. So the derivative of 2y, that would be 2. f prime of g, right? So f prime derivative of cosine is minus sign. There's a minus sign here. So it's minus sign of g. So it's a minus sign of 2y. Right? So that will be equal to 2x. There's this minus sign. So it's a minus 2 sine of 2y. Right? So you see, guys, in this case, derivative of n with respect to x is equal to the derivative of m with respect to y. Okay, so the conclusion here so derivative of n with respect to x is equal to the derivative of m with respect to y, and so the vector field f is a conservative vector field or gradient vector field. So f is conservative. Okay. Any question, guys? So if you don't have any trouble with the partial derivatives, then you should be okay with this exercise, I guess. Now for number 3, that's a 3-dimensional. So for number 3, so let me just write down again the f. So f, it's actually, so we have x over x squared plus y squared plus z squared minus 6x. Second component is yx squared plus y squared plus z squared, z over x squared plus y squared plus z squared. Okay. So what will be the domain of f here in this case? Well, there's only one trouble here, is that of course we are not allowed to divide by 0. And here in the denominator we have this x squared plus y squared plus z squared. So the question is, when x squared, x squared plus y squared plus z squared is equal to 0, right? Well, the answer is, x squared, this is supposed to be positive of 0 plus another positive of 0 plus another positive or 0. So the sum is equal to 0. It means that each term is equal to 0. So the x squared is equal to 0, and the y squared is 0, and the z squared is 0, right? So actually we can conclude that the x is equal to y is equal to z is equal to 0, okay? So all of them, they have to be 0, okay? So the domain of f here, it's just, so we have to remove from the domain the origin, right? That's where x and y and z are 0. Okay, so the domain of f is R3 minus, so we have to remove, this is minus, so we remove the origin, right? That's where x and y and z are 0. Okay, and I claim that R3, the space minus 1 point, is simply connected, right? So because again, the idea basically is to check if the space is just a one single piece, and that's the case of R3 minus 1 point, just a one piece, right? And we have to check that there's no hole in the space, right? So here there's no hole. It's we are removing just 1 point, so it's not a hole in R3, right? So this is, it's simply connected. Okay. Anyway, so we have to, to determine whether f is conservative. So we have to compute the curl of f. So curl of f, that would be the cross product of the del operator with the vector field f. So we have I, j, k. Del operator, well, that would be partial x, partial y, partial z. The f, first component, we have this x over, x squared plus y squared plus z squared minus 6x. This is a first component. Probably I need more space here. I guess I need more space, so I'm gonna just erase this, and so I'm gonna put the J probably here and the K somewhere here. Okay, so this is here's partial Y, and here's partial Z. Okay, so then the second component is just Y over X squared plus Y squared plus Z squared. And the third component is Z over X squared plus Y squared plus Z squared. All right. So what will be the curl of F? So we start with I. So this is equal to, so here's my I. So the coefficient of I would be, so for I, we have to cross multiply. So this partial Y with the, so that will be the derivative with respect to Y of the Z over X squared plus Y squared plus Z squared. Okay. Minus, and then here that will be derivative of with respect to Z minus the derivative with respect to Z of, so Y over, X squared plus Y squared plus Z squared. Okay. So that's the coefficient of I, coefficient of J. So for J, we need to take so here, the derivative with respect to Z of this function here, right? So that's derivative with respect to Z of X over X squared plus Y squared plus Z squared minus 6X minus, and then we take the derivative with respect to X of this function here. So that's minus partial X of the Z over X squared plus Y squared plus Z squared. And the last component K. So for K, I'm gonna cross multiply these terms here. So that's partial X, Y over the X squared, Y squared Z squared, minus derivative with respect to Y of the X over X squared plus Y squared plus 6Z squared, sorry, minus 6X. Okay. All right, guys. So we want to compute the partial derivatives here. So for example, I mean, like it seems like a long computations here, but anyway, let me just say here, like for the first partial derivative, this one here, it's partial derivative with respect to Y of Z over X squared plus Y squared plus Z squared. So the Z is we assume X and Z as a constant, right? So there's a Y here in the denominator, right? So that you have two options here. Mainly, you can, well, either you apply, the quotient rule, or you can just say, this X squared plus Y squared plus Z squared is in the denominator. So if you move the X squared plus Y squared plus Z squared to the top, that will be with the power -1, right? And then you can just apply, the power rule for derivative. So I mean, it's up to you. There are different ways here to compute the partial derivative. So let's just apply, if you want to apply the quotient rule, that would be probably easier. But anyway, it's up to you guys. So like here for this partial derivative, if you apply the quotient rule, Z is a constant, right? So the derivative of Z is just 0 minus, right? So we're gonna need the derivative minus Z times the derivative of the bottom. So it's minus Z times 2Y over the square of the denominator, right? So over X squared plus Y squared plus Z squared. So again, here I just applied the quotient rule. And when you apply the quotient rule, the Z is a constant, the derivative of Z is 0. So that's why you have this minus, okay? Quotient rule, okay? So minus here the same. You're gonna have, there's a Z, derivative with respect to Z There's no z in the top. That's a good news. So there's only z in the bottom. You can apply again quotient rule. So that will be minus. So y is a constant. Derivative of y would be 0. So that will be minus y times the derivative of the bottom with respect to z. So that will be 2z. Okay, over the square of the denominator. I forgot the square here. The square of the denominator. Okay, and that's times the I. All right, for J, it's almost the same thing here for J and for K. So for derivative with respect to Z, well, of this thing here, 6x is supposed to be constant, so the derivative of that will be 0. And derivative of this fraction here, again, you can just apply quotient rule. And derivative of x at the top, the function at the top is just 0, so there'll be just minus the function in the top, x, times the derivative of the bottom with respect to z. So that's 2z over the square of the denominator. Okay. Anyway, guys, if you're having trouble with partial derivatives here, just let me know. All right. So for the derivative with respect to x of this z, etc., the same thing. So we're gonna have minus z derivative of the bottom, which is 2x, the square of the denominator. Right. And for the third component, coefficient of k, derivative with respect to x, again, it's minus y times 2x, the square of the denominator, minus, well, same thing, it's minus, so the derivative with respect to y, so it's minus x times 2y over the square, again, of the denominator. And derivative of 6x with respect to y, of course, x is assumed to be constant, so then that will be just 0. All right. Anyway, so you can see here, because of the minus, so this minus, there will be a plus. This is a minus, another plus, same thing here. And you can see, so for the first component, this thing here is going to be just 0 because there is a minus here, plus. Second component, same thing. Here is a minus and there's a plus. It's of the same thing, so it's going to be 0. And here's the same. It's going to be 0. So actually, the curl of the vector field is just the 0 vector. Okay. I mean, the partial derivatives, they seem like kind of difficult, but they are not. You just apply the quotient rule and it will be fine. So conclusion is that, of course, that this vector field is f is, so curl of f is the 0 vector. So f is a conservative vector field. Okay, so f is conservative. All right, guys. So before the answer to the second question, remember the second question was assuming f is conservative. How can we find the potential function f? Let me just make a couple of remarks here. So first remark is that, so if you take this vector field f, so I'm gonna make a couple of remarks using this vector field, the last example, last exercise, last problem. So we have this vector field f, right, which is, x over x squared, y squared plus z squared minus 6x, y over same thing, and z over the same thing. Okay. Now, let's say you have some path gamma. Okay, you have some path gamma from, so gamma of t, let's say gamma of t is, let's say 1 minus t, sine of pi of t, and last component is t, okay, with t in the interval, let's say 0, 1, okay. Let's say you want to evaluate so we just proved that this vector field F, of course, is a conservative, right? But we don't know yet how to find the potential function F, right? But so let's say now we want to evaluate, the vector line integral of this vector field F along gamma. Okay. So this would be equal, so we know how to compute this vector line integral. So this would be equal to, as you know, this is just a f of gamma of t, right? Scalar product with the tangent vector gamma prime of t, which is the tangent vector to gamma, to the path gamma, right? Scalar product here, gamma prime of t, dt, right? T is in the interval 0, 1. Okay. So anyway, so if you evaluate this scalar product of f of gamma of t with the gamma prime of t, then this would be equal to 0, 1. So you're going to end up with the following integral. So you're going to end up with so here I'm jumping a couple of steps. So all I'm saying is, if you evaluate this f vector field F at along gamma of t, scalar product with the tangent vector to the path to the path gamma, right? Then you're gonna end up with, so here I'm jumping a couple of steps because we know, guys, how to compute this vector line integral, right? Anyway, so you end up with this integral like 2t minus 1 plus pi cosine of pi t, sine of pi t over like 1 minus t squared plus sine squared of pi t plus t squared, right? Because of the x squared plus y squared plus z squared. Remember that the x is equal to 1 minus t. The y is supposed to be equal to sine of pi t, and the z is just equal to t. Minus or plus, I think, plus 6 times 1 minus t dt. Okay. Anyway, so my point is, if you evaluate this vector line integral, so you're going to end up with this crazy integral here, right? And this integral here is it's really tricky to evaluate. Okay. It's going to take you like probably the whole day just to evaluate this integral. So this is tricky to evaluate, right? Okay. And well, we do know that F is conservative, right? But we don't know how to find yet the potential function F, right? Because if we know how to find the potential function F, then we can just use the fact that if F is conservative, then it's path independent line integral, and so this integral would be just the difference. So you have to evaluate your potential function at the endpoints of the integral of the path, right? But the thing is, well, but we do know that F is conservative, right? So if it's conservative, it means that it's it's path independent line integral. So what we can do, guys, here is, we may choose another path instead of this gamma. We may choose another path with the same endpoints. Okay, so because this is tricky to evaluate, so we're gonna find another way to evaluate this integral. So what we're gonna do, well, we know that this F is conservative. Right? So F is path independent line integral. So we may choose another path with the same endpoints. So for example, here, what are the endpoints of gamma? What's gamma of 0? Well, gamma of 0 is just 1, sine of 0 is 0, and 0. So gamma of 0 is 0, 1, 0, 0, sorry. So gamma of 0, gamma of 0 is what if the point is the point 1, 0, 0. What's gamma of 1? Well, let's see. If t is 1, we're going to have 0. Sine of pi is 0, and third component is going to be 1. So it's gamma of 1 is 0, 0, 1, right? Okay, so what we are saying is we have this path gamma from, so this is 1, this is x here, this is z. So this is the point gamma of 0. Let's call this point the capital A, which is 1, 0, 0, right? And capital B, the terminal point, it's gamma of 1, 0, 0, 1. So this is, let's say, capital B. This is gamma of 1 and 0, 0, 1, right? And we have this path gamma. And so we are moving from, from gamma of 0 to gamma of 1. So all I'm saying here, guys, so what we can do in this case, because when you want to evaluate this vector line integral, and it's tricky to evaluate. So what we're gonna do, we may choose another path from A to B, okay, which would give you like a very simple vector line integral, okay. So like in this case, in your vector field F, you have this x squared plus y squared plus z squared, right? So probably a good idea would be just to use use a cosine and sine, because cosine squared sine plus sine squared will be 1. So what I claim is that, so if you pick, let's say, so I'm going to pick another path, let's say beta of t equal to cosine of t, 0 and sine of t. Okay, and let's say t between 0 and pi over 2. So my point here is that beta of 0, that's cosine of 0, that's 1, 0, and sine of 0, that's 0. So beta of 0 would be a, that's the point 1, 0, 0. That's the same as gamma 0. Okay, and beta of pi over 2. So cosine of pi over 2 is 0, 0, sine of pi over 2 is 1. So that's gamma of 1, which is the terminal point B, right? So here I have this path beta moving from A to B, right? And so you may ask why I choose again this cosine and sine, because I want to evaluate this vector line integral with this vector field F. And the thing is, in the vector field F, there is this x squared plus y squared plus z squared. So if you choose the cosine and sine, then that would give you, cosine squared plus sine squared, that would give you 1, right? So that'll be very simple. That's going to simplify the expression of f of beta of t, right? So anyway, so what we can say here is that, so the vector line integral of f along gamma is actually equal to the vector line integral of f along beta, right? Because again, so here I'm using the fact that f is path independent. Okay, so my vector line integral is going to be the same along gamma and beta, right? Because they connect the same, they have the same initial point and the same terminal point, right? Now, so this is just f of beta of t, okay, scalar product with beta prime of t. So this is beta prime of t, dt, t from 0 to pi over 2. Now, as I said, well, I mean, this would be equal to, I mean, f, remember f, we said f is, you know, I think it's what? Yeah, it's x over x squared plus y squared, you know, plus z squared minus 6x. Same here for y, same denominator, right? That's my f, and here's my z, my third component, same denominator, the z in the top, okay? And beta of t is just, you know, cosine 0 sine. So now, so when you evaluate this vector line integral, so f of beta of t, so x is cosine, so there's going to be cosine in the top, cosine of t, over, and cosine x is, so x is cosine, right? This is my x of t, y of t is 0, and z of t is sine of t. So when you do the x squared plus y squared plus z squared, that will be cosine squared plus 0 squared plus sine squared, and that will be equal to 1. So here it's over 1 minus 6x, so that's minus 6 cosine of t. The second component, y, is just 0, so the whole thing is going to be 0. And the third component is z, that's sine of t, over the same cosine squared plus sine squared, that will be 1. Okay, scalar product with the derivative of the tangent vector to the path beta. Derivative of cosine, it's minus sine. Derivative of 0 is 0. Derivative of sine is cosine. Okay. So this is, of course, from 0 to pi over 2. So this would be equal to the 0 pi over 2. So cosine minus cosine of t minus 6 cosine of t, right? That would be minus 5 cosine of t times minus sine of t, and then plus 0, and then plus sine of t cosine of t, dt. So this is just the integral of, so minus here would be a plus. So 5 cosine sine plus another sine cosine, so that'll be 6 cosine of t, sine of t, dt. Okay. And this integral is kind of very easy to evaluate. You know, you can either use a trig identity, right? Or you can just say, you can just use a substitution here. U is sine of t. So then derivative of u, it's cosine of t, right, dt. Okay, so you can just use a substitution here. And so if you use a substitution, then that will be equal to just 3 sine square of t, t between 0 and pi over 2. So that will be equal to, so sine of pi over 2 is 1, sine, so 1 squared is 1, so 3 times 1, so that will be equal to 3 minus sine of 0 is just 0, so the answer would be just 3. Okay. So you see here, guys, the point here is that I had this very tricky integral to compute, but because I can use the fact that the vector field is path independent, so I may choose another path. And if you pick carefully your new path, then your integral, your vector line integral is going to be kind of easy to evaluate. All right. Any question, guys, about this remark? So all I'm saying here again is just because your vector field is path independent, so you can pick any path, you know, with the same terminal initial and terminal point, right? So then sometimes you have very tricky integrals. So all you have to do is just to change the path. All right, now let's answer the second question. So The second question was, if your vector field is conservative, how can we find this potential function f, right? So I'm gonna do a couple of examples. So question number 2, just let me write down the question number 2. So assuming the vector field, so f, assuming f to be conservative, so is conservative. Okay. How can we find the potential function f? Okay, how can we find the lowercase f? Okay, now let's do an example. So first example, I'm gonna come back to the exercise here. So in the problem number 2 in the exercise, where is it? So problem number 2 in the exercise, we had this, where is it? Here. Where is it? Exercise here. Okay. So in number 2 in the exercise, we had this, we had this vector field f, and we checked that f is actually a conservative vector field, right? Now, so in my first example, we're gonna try to find the potential function f for which this vector field f is equal to the gradient of the function, right? So first example, so my first example here. So examples. So example 1. So I'm going to start with a 2-dimensional example. So this is again the same vector field we have in the exercise. So f is just a 2xy plus cosine of 2y, and then x squared minus 2x sine of 2y. Okay. So in the exercise, so we check, so we know that f is conservative. Okay. We know that f is conservative by the previous exercise. We check that the derivative of n with respect to x is equal to the derivative of m with respect to y. Okay, so now the question is exercise. Okay, so f is the gradient of some function f, right? So how can we find f? Well, so if, well, f is the gradient of f, it means that actually f is supposed to be equal to the derivative of f with respect to x and the derivative of the function f with respect to y. Okay, so in other words, the first component, this is supposed to be derivative of my function f, potential function f with respect to x. Second component is supposed to be the derivative of function f with respect to y. Okay, so what I'm gonna do, guys, we're gonna try like to integrate. Okay, so we know, so what we know is the following. So we know the following. So we have two equations. I know the derivative of my potential function f with respect to x is the first component. And I know that derivative of my potential function f with respect to y is the second component, which is the x squared minus 2x sine of 2y. Okay. So I have these two equations. Now I'm going to use these two equations to find my function f. So first equation, so what I'm going to do, I'm going to integrate. So let's integrate. So step 1, so here we're going to have 2 steps. So step 1, so we're going to integrate the first equation. Integrate 1 with respect to x. Okay, we know it's the derivative, that's the derivative with respect to x, right? The first equation, right? So we're going to integrate with respect to x. So when you integrate, so we're going to have your function f. So it's a function of two variables, x, y. So what will be the integral of 2xy with respect to x? Again, we assume that y is constant because we integrate with respect to x, right? So then y here is, we assume that y is constant, right? When you integrate with respect to x. Okay, so we don't really worry about the y, it's just constant. The 2 also is just a constant. So all you have to integrate here is just the x. But the integral of x is x squared over 2. So x squared over 2, and there's times 2 here. So the integral with respect to x will be x squared times y, right? Because when you derive with respect to x, it's going to be 2xy. That's exactly what I have here. Now, for the second component, it's cosine of 2y, right? And y is a constant. So this cosine of 2y is just constant. And what will be the integral of constant with respect to x? It's going to be the constant times x. So that will be plus x cosine of 2y. Okay. Plus, and then remember, guys, when you integrate, so when you are done with the integration, then at the end, you're supposed to add a constant, right? Because the derivative of a constant is a 0. Okay, so usually we're going to put like constant here when you integrate, right? But here you need to be careful. So it's not just a constant here, but it's going to be, because remember, guys, y is supposed to be constant, right? So any function of y is going to be constant. So the constant in this case, it's not just a number, but there's going to be some function of y. So here it's plus g of y. Okay. So because when you derive some function of y with respect to x, well, that function of y is going to be just constant. So the derivative would be just 0 with respect to x. Okay. So my function f, so when you integrate 1, you get this x squared y plus x cosine of 2y plus this function of y. Again, I have this function of y because derivative of this function of y with respect to x is going to be 0. Okay, so it doesn't change your derivative. So any function of y doesn't change your derivative. Okay, now, so the problem is, what's this function of y, right? And that's where we're going to use the second equation. So step number 2. So what we do is we derive f of xy obtained in the step 1. And compared to derivative. So we derive f obtained in the first step with respect to y, of course. So this is with respect to y. With respect to y. And compared to the equation number 2. Compare it to 2. Okay. So if you derive the function f obtained in the first step with respect to y, then we're gonna have, so derivative with respect to y of my function f obtained in the first step. So this is the function f in step 1. Okay. With respect to y, so then x is constant. So derivative of x squared y with respect to y, that will be just x squared. And then derivative of x cosine of 2y with respect to y, that will be, x is a constant. Cosine of 2y, we need to use the chain rule. So that's minus 2x. Derivative of cosine is minus sign. So that's why I have this minus sine of 2y. Plus, and then derivative of this function g of y. I mean, we don't know what's the function g of y. So derivative of g of y with respect to y is just g prime of y. Okay. It's just g prime of y. So this is supposed to be a derivative of my function f with respect to y. Now we need to compare it to the equation number 2. So we know that this is supposed to be equal to, so by equation number 2, we know that this is supposed to be equal to this function here. So this is equal to this x squared minus 2x sine of y. Okay. So now if you compare these two functions, I have x squared here, that's perfect. I have this minus 2x sine of y, minus 2x sine of y. Okay. So then it means that this g prime of y is just 0. So then g prime of y is just 0. So then I have a function of y, the derivative of my function of y is 0. So then the integral g of y is going to be just a constant. So this is equal to some constant c constant. Okay. Derivative is equal to 0. So then the integral is just a constant. Here it's just a constant because this function g is just a function of one variable, which is y. We don't have x here, it's just y here. Okay, so integral of a 0 is a constant. So now I can say that this function, this mysterious function g, this unknown function g is just equal to constant. So my function f, so the conclusion here is that my function f is this x squared y plus x cosine of 2y plus g of y, which is actually turns out to be just a constant. Okay, so the answer here, my potential function f is just x squared y plus x cosine of 2y plus a constant c, where c is a constant. That's my potential function f. So then you can see, guys, that you can check that my vector field f is derivative of this function f lowercase f with respect to x, lowercase f derivative with respect to y. Okay. So that's my potential function f, right? So all you have to do is just to integrate. Any question, guys? So, I mean, this is a two-dimensional example. Let me do a third, three-dimensional example. So another second example, example number 2. And in this example number 2, I'm going to come back to this, let's say, or I'm going to use a different vector field. So let's say f is e to the x times sine of y minus yz, e to the x cosine of y minus xz, and then z minus xy. Okay, this is my vector field f. All right. Well, I claim that this vector field is, I don't think we checked that this vector field is a conservative vector field. Not in the previous exercise, I don't think so. Yeah, so I claim, I mean, you can check it, of course, at home. So this f is a conservative vector field. Okay, so f is the gradient of some function f. Okay, again, all you have to do is to compute the curl of f, right? Which actually is going to be 0, the 0 vector. Right, so now we are interested. So we know that this vector field f is a conservative. Okay, so we need to find this potential function f. All right, so this is a three-dimensional vector field, which means that the function f the potential function f is, so f is a function of three variables, right? X, Y, Z. And what we are saying is that the first component here, this is supposed to be derivative of f with respect to x. The second component, this is supposed to be derivative of f with respect to y. And the third component is supposed to be derivative of f with respect to z, right? So here, in this case, we have three different equations. Okay, so we have three different equations. We know the derivative of f with respect to x is the first component. We know that the derivative of f with respect to y is the second component. And we know that the derivative of f with respect to z is the third component, which is z minus xy, right? So again, the goal is to find this function f. We know the derivatives of f with respect to x, y, and z. So we need to find this function f. Well, so the steps here, we're going to have, I would say, 3 steps because we have like 3 different equations. So first step, step 1, we have to integrate the first equation with respect to x. So the first equation is the derivative with respect to x. So we're going to integrate 1 with respect to x. Okay. So when you integrate, well, it's a derivative of f with respect to x. So when you integrate, you're gonna find the function f. So you're gonna have your function f. Now, what's the integral of this e to the x sine of y? So when you integrate with respect to x, you assume that y and z are constant. Assume y, z as constant. Okay. So sine of y is just constant. We don't worry about the constant. So we just integrate e to the x. Integral of e to the x is just e to the x. Okay, so that's e to the x times the constant sine of y minus. And then the second term here, yz times y times z, both are constant. So the whole thing is just constant. And integral of the constant with respect to x, it will be the constant times x. So that will be minus y zx. Minus y zx, right? And then we are done. We are almost done, actually. Plus, so again, when you integrate, you're supposed to add a constant at the end, right? But here, we are integrating with respect to x. So which means that y and z both, they're supposed to be constant, right? So what will be a constant in this case when you integrate with respect to x? So the constant here would be some function of y and z, right? Because both y and z are constant. So here it's going to be some function g of y and z both, right? Because what will be the derivative of this function with respect to x? Well, it's just a function of y and z, and both are constant, so the derivative would be 0. So it doesn't change the derivative of f with respect to x. It's going to be just 0. Okay, so here in this case, when you have the 3 variables and you integrate with respect to x, the constant would be some function of y and z, not just y, not just z, but the function of y and z both. Okay, because both of them are constant when you integrate with respect to x, or when you derive with respect to x. Okay. Now, in the step number 2, so we're going to derive this function here with respect to y, and we're going to compare it to the second equation. So derive with respect to y. Of course, when you derive with respect to y, x and z assumed to be constant, and we have to compare it to 2, because the equation 2, that's supposed to be derivative of f with respect to y. So what's the derivative of this function f here with respect to y? So derivative of f x, y, z, this function f here with respect to y, this is going to be equal. So e to the x, so first I have e to the x sine of y derivative, x is a constant. Derivative of sine of y is just cosine of y. So that'll be e to the x cosine of y minus, and then what will be the derivative of yzx with respect to y? So it's going to be just the constant zx. So it's minus zx plus, and then derivative of the function g of yz with respect to y, right? So plus derivative of this function g with respect to y. Again, we don't know yet what's this function g of yz. So now I'm going to compare it with the second equation. So the second equation, it's supposed to be this second equation here. This is supposed to be derivative of f with respect to y. So this is supposed to be equal to the second equation, number 2, which is ex cosine of y minus xz, right? And that's it. Now, if you compare these two functions, so here we have the same thing, e to the x cosine of y, e to the x cosine of y. You have that's minus zx minus xz, right? So which means that this derivative of this function g of yz with respect to y is 0. Okay, so this means, so derivative of g of yz with respect to y is just 0. So what will be then the function g of yz? Well, if the derivative with respect to y is 0, it means that the function g of yz is not just a constant, but it's going to be some function of z. Because, so when you derive here with respect to y, if you have some function of z, then derivative with respect to y would be 0, right? Derivative of this with respect to y would be 0. Okay, so in this case, so my function is some function of z. Okay, because it's derivative. So what we are saying here, derivative with respect to y is 0. So it must be a function of z, because z is a constant when you derive with respect to y, right? So from this step number 2, what we are saying, so we have more information about this function g of y is z. So it turns out from this step number 2, so what you're saying here, so my function f, it's so e to the x sine of y minus yzx, and this function g of yz turns out to be some function of just of z, right? So this is plus a h of z, right? Okay, so we still need to find this function h of z. And that's where we're going to use the third equation. So step number 3, now we're going to derive with respect to z, and we're going to compare it to the equation number 3. So we're going to derive with respect to z, derive f, of course, the f we get from step number 2, this f here with respect to z, and compare it to equation number 3. Okay, so what will be derivative here of this function f that we got in the step 2 with respect to z? So derivative of f with respect to z. So derivative of e to the x sine of y with respect to z, everything is constant, so it's going to be just 0. Derivative of yzx with respect to z, it's yx, so it's minus yx, plus derivative of h of z with respect to z, so it's going to be h prime of z. Okay, and this is supposed to be equal to the equation number 3, because the equation number 3, that's the derivative of f with respect to z. So what's the equation number 3? So we said, here's the equation number 3. So derivative of f with respect to z, that's supposed to be equal to z minus xy. So this thing here, this is supposed to be equal to the z minus xy, equal to z minus xy. Okay. So now if we compare the two functions, Well, we got minus yx minus xy. That's the same thing, right? And then, well, there's a 0. We don't care about 0. And so the conclusion here is that this h prime of z is equal to z. Okay, so h prime of z is equal to z. So here we have this function h is just a function of z. So we have only one variable, right? So when you integrate z with respect to z, it's just z squared over 2 plus some constant. Some constant here. Okay. So what we are saying is that this function h of z is actually z squared over 2 plus constant. So now, if we come back to my function f, so now we know that this function h of z is actually z squared over 2 plus constant. Okay, so then this would be my function f, potential function f. So it's e to the x sine of y minus yzx plus z squared over 2 plus some constant, right? So find the answer. Conclusion here. So my function f, xy, so is e to the x sine of y minus xyz plus the h of z, which is z squared over 2 plus constant. Okay, so that's a fine answer. That's my potential function f. All right. So any question, guys? So you see how it works. I mean, we have like in this like three-dimensional case, we have like 3 equations. So we're gonna have like 3 different steps. First step, you integrate the first equation with respect to x. The second step is you derive the function you get in the first step with respect to y, and you compare it to the second equation, right? Then you're gonna end up with a new function f. And then in the third step, you're gonna derive the function f you get in the second step, and you compare it to the equation 3. Okay. All right. Well, anyway, if you don't have any question, guys, well, we still have like 2 minutes. So what I'm gonna do, I'm gonna write down exercise here for you. Find this scalar function f. But of course, we won't have time. I don't know. We'll see if next time if I'm gonna go over the exercise or not. But this thing here is gonna be, of course, included in the homework number 5. Okay, so let me write down this exercise for you. I mean, if you have time at home and you want to practice a little bit. Again, this is going to be also in the homework anyway. So, but here's here's an exercise. So you need to find the scalar potential function f. So all these vector fields, of course, they are conservative. We know that the gradient of some function f. So first vector field is, so f is xy. Let's say this is, or f of xyz. Let's say. Is equal to 3x squared. We already checked, I think, in this in the exercise, in the previous exercise, we already checked that this vector field is conservative, right? So this is 3x squared, z squared over y, and then 2z natural log of y. So we know that this vector field is conservative by the previous exercise, so we need to find the potential function f. And number 2, remember we had this long vector field with the x squared plus y squared plus z squared. So here you need to find the potential function of this vector field. So x over x squared plus y squared plus z squared minus 6x over minus 6x. Second component is just y over x squared plus y squared plus z squared. So all you have to do, guys, again, to integrate, you have to integrate. Here you can see in the bottom you have x squared, in the top you have x. So like you have the derivative of x squared in the top. So you can just use a natural log here. Anyway, so the third component is z over x squared plus y squared plus z squared. All right, guys. So, I mean, this is for you if you want to practice a little bit. And again, this is going to be included in the homework anyway. So I'm going to stop here, guys. So next time, I'm going to either going to start a new section, or I'm going to go over this exercise if you have still trouble with this this kind of problems. Okay, if you have problem with this kind of exercise, just let me know next time, and I will go over this exercise. All right. So yeah, so I'm gonna stop here, and I will see you, I guess, next Tuesday. So I'm gonna stop, I guess, recording.